Now we turn our attention to linear regression. We want to actually be able to predict y from x. We want a mathematical model describing the relationship between y and x. This lets us understand the nature of the relationship and make predictions. So we're going to focus on linear models, the creation of lines that fits the data as well as possible. This is called linear regression. And there are more complicated models when the scatter plots don't look like a line, but this is a great place to get started. So here's price versus size for houses, and it sure looks like a straight line would not do a horrible job of fitting the data. So we're looking for a model of the form y hat equals b0 plus b1x, and we want the one that best fits the data. So y hat here is the predicted value of y given an x. b1 is called the slope of the line. And what the slope of a line tells you is as x changes by 1, a predicted y changes by b1. b0 is the intercept. It's the predicted y value when x equals 0. So this is a general fact about how lines work, which we may review in class briefly. So we're looking for the b0 and the b1, which gives the best overall fit. So the one that works for this example, and I think it's different data now. Actually, no, it's the same data. Y hat equals 15 plus 0.105x. So price in thousands, the predicted price is 15 plus 0.105x. And what is all that telling us? Well, the slope, that's the multiplier of the x, it's called the coefficient, is 0.105. And that says for every additional square foot a house has, the predicted price increases by $105. Why $105? Because remember, y is measured in thousands, and so 0.105 thousandths is 105. Okay, so the slope tells us for every additional square foot a house has, a predicted price for it goes up by $105. The intercept is 15. It's trying to tell us the predicted price of a 0 square foot house is 15 or $15,000. And that's just not meaningful in this case. There's no such thing as a 0 square foot house. Almost always the slope of a regression line is meaningful. The intercept may or may not be. And as an example of how we would use this model, in this community, the predicted price of a 2,000 square foot house is $225,000. Because if you take 15 plus 0.105 times 2,000, you get 225. So that line, 15 plus 0.1x, I'm throwing away the 0.5 now, that line is the line that best fits the data. But best meaning what? Well, for each home of some size, there's an actual price and a predicted price. And that difference, if we look at our actual data set and saw how well the line predicted it, the difference between what the line predicted and the actual price is called the residual. It tells you how far off your prediction is. And we choose as our best fit line the one that makes the sum of the squares of the residuals as small as possible. So that's a lot to wrap our heads around, but basically once you have any line, it makes a prediction for each house in your actual data set. And we can estimate sort of the total amount of error by seeing how far off we are for each house. Squaring those numbers is mathematically convenient and makes them all positive. So we see how far off we are and add them up, and the one that makes that total error as small as possible, that's what we mean by a regression line. It's the line of, it's the least squares regression line is what it's called. And here's how we do it in Excel. Again, a separate screencast to explain that. Now, often there's more than one explanatory variable, which we expect to affect the response variable. That ought to make sense. Anything we're interested in predicting or studying doesn't depend on just one other number. So we're now looking for a model of the form y hat equals b0 plus b1x1 plus b2x2, etc. And again, the best is the one with the smallest sum of squared residuals. And with the help of Excel, we can get multiple regression models. And let's just look at an output to start to see what's going on here. So this is the multiple regression model predicting the price of a house in Bristol, Wisconsin from its size, how many square feet, and the number of bedrooms. And the output that Excel gives us has a lot of stuff, but the parts we need is just down here in the lower left-hand corner, and let's see how to turn this into a model. So there's that lower left-hand corner. It's telling us that the predicted price, the thing we want to predict, is 36,783. That's our intercept, plus 157 times the total square feet, plus, or actually minus 42,073 times the number of bedrooms. And here the price is not in thousands, it's in the actual price. So if you want to predict a price of a home in Bristol, take 36,783, add 157 times the total number of square feet it has, and subtract off 42,073 times however many bedrooms it has. It's kind of curious. It looks like the more bedrooms it has, the cheaper it costs, minus 42,073. Why might that be? See if you can puzzle it out. Why would more bedrooms mean lower price?